used in gas chromatography. And then after that, before that, we also talk about gel permeations and then HPLC. And then if you look at here, actually the gas chromatography was quite advanced before the HPLC was first come to the market. So 1969 is the first HPLC apparatus being commercialized in the market. And then after that, in 1975, the ion chromatography. So which in our next week's seminar, I will talk a bit about ion chromatography. And then I will also talk about how we synthesize not only ion chromatography, but also the other materials for color materials. So which is what we normally do in our lab. So I will share about how we synthesize the color materials. I remember last time in our HPLC classes, some of the students asked about how we synthesize the materials. So we will share a bit how we make the capillary columns here. And then if you look at here, in 1979, the fused silica capillary was invented in the market. Yeah? Invented means was commercialized in the market. Maybe you still remember I showed you the capillary last week. The fused silica means this fused silica. Yeah? So it's capillary. So after this fused silica was sold by a company, the applications of capillary just boom, just jump very high, especially in the field of electrophoresis. Well, of course, the capillary LC also, but at the time, later I will also, explain why is it capillary is so important. I think we talk about it many times before to reduce the Van Dimter effect and to have better separations. We need to reduce the size of the laminar flow. Yeah? So if you look at the history here in 1981, capillary zone electrophoresis, and in 1984.
Excuse me, Prof. Have you shared your slide before? Because here is, I cannot see your slide.
Oh, really? It's not sharing?
Yeah.
そうなんだ。
Okay.
ごめんなさい。
Okay.
So that means I have been talking without sharing.
From the start, I guess.
ごめんなさい. It's so embarrassing. Yeah?
It's okay, Prof.
Sorry. Hi. And anyway, hi. Okay. So okay, so in 1979, so this is the inventions of the fused silica capillary. Then after that, three very important techniques were invented. In 1981, the capillary zone electrophoresis. Then in 1984, the missile, using the missile like surfactant, electrokinetic chromatography. And then recently is the combinations between the capillary zone electrophoresis and liquid chromatography. So we call it capillary electrochromatography. Yeah? So from here in 1984, and I mean the MCEK, we call it MCKC, yeah? MEKC and the CEC. At the last of the name is chromatography, means it's involved some kind of like stationary phase. Yeah. So some people say electrophoresis is not chromatography. Yeah? And so it's depending on individual. Sometimes the definitions is different. So the people who are doing electrophoresis, they say, I'm not a chromatographer, I'm doing electrophoresis. Yeah. So anyway, actually, before all of this, the first phenomenon of the electrokinetic was actually founded much earlier in 1807 by a Russian. We call it Vils. So he was from the Moscow State University. So at the time, he found that when he passed by a constant electric field and the clay particles dispersed in water was started to migrate. So well, clay is a form of, like a sand, and sand is also is a form of like a silica. Yeah? So that means when there's a silica, that means there's a silano group, that means there's a negative charge or something like that. So when there's a charge, when there's the electricity with a plus and negative, it means a charge. So something will start moving. Yeah? So that was the first electrokinetic phenomenon that was found by used at the time. It's very earlier in the 19th century. But when we talk about electrophoresis, the person that usually we remember is this gentleman. The name is very long, but we just say Tiserius. So he is the father of electrophoresis. So last time, I talked, Martin got the Nobel Prize, and this Tiserius also got the Nobel Prize in chemistry as well in 1948. But the person who are doing pure liquid chromatography, HPLC or Z was recommended for Nobel Prize, but he didn't get Nobel Prize. I mean, if he was alive, maybe he could have, but he died very young. So, and then one of the requirement of Nobel Prize is you cannot die. They don't give Nobel Prize to people who already died. So, and Z didn't get Nobel Prize. But this father of electrophoresis, he got the Nobel Prize in 1948. If you look at the reason why he got a Nobel Prize is for his research on electrophoresis and absorption analysis, especially for the discoveries concerning complex nature of serum proteins. Yeah? So the first thing is electrophoresis. Yeah? So at the same time, I think he got his PhD in quite early, like in 1930s, around 1930s. So he got his PhD in, I think maybe in Uppsala University, which is the oldest university in Sweden. And he is a Swedish biochemist. Yeah? So his PhD was about electrophoresis. But after his PhD, for a few years, he was doing something, maybe you heard of the name zeolite. He was one of the earlier persons who investigate the absorption phenomena of zeolite. Yeah? So like how is the desorption and then the absorption and also desorption of the main components on zeolite. So this is also part of his research. But he was more popular for electrophoresis because he managed to separate serum proteins. Yeah? So serum, maybe you know serum, it's is our part of our blood. You know our blood, right? So we have the red blood cell, and then we have the white blood cell, and then we also have the platelet, which is the clotting agent, and then beside that there is a serum. Yeah? So serum, it's a liquid form in our beside the cells. So serum is the plasma of our blood. So 90% of serum is water, but about 7% is protein. Yeah? So, and then that's why he was able to separate the complex, a few serum proteins. So if you Google serum proteins electrophoresis, which is this one, so and this one is very popular. Yeah. So when people talk about the earlier electrophoresis is the serum protein electrophoresis. So Tiserius managed to separate the proteins between the first one, the biggest one here is albumin. So about 30% or sometimes it's 30-40% is albumin. And then here is like alpha 1, alpha 2, beta, and then gamma. So alpha, beta, gamma, it's all from globulin. So globulin, so the main components of the blood, the serum protein is albumin and globulin. So globulin, it's mainly for like to bind with hemoglobin for example, if we have some like the vaccine or whatever, so the antibodies will be transported by the like the gamma albumin, yeah. So I mean gamma globulin. So albumin, it's more like to transport some other things also, but the globulin is divided into alpha 1, alpha 2, beta, and gamma. So this graph is quite popular, and it is very easy to remember if you we call it the right hand sign like this. Yeah. Maybe you see this the people in the Hawaii, the aloha sign. So if you look at the graph here, it looks like your hands like this, you know. So if you look at your right hand, the your the smaller fingers is the albumin, yeah. Then the rest is the alpha 1, alpha 2, beta, and gamma, yeah. So you can use this the right hand slow to remember this serum protein electrophoresis, yeah. Anyway, okay, all right. So anyway, like I said, there are many types of electrophoresis. So some of the main one will be like this, like the agarose gel electrophoresis. And then we also have, well, the main thing is whether the electrophoresis is with a support or without a support. Yeah. So like for example, capillary electrophoresis is without any support. It means it's just no medium, just free solution, just only solutions. Yeah. So, but other things like agarose gel, that means there is a support, there is a medium. We use the gel. And then this one also gel, you know, if you look at here, most of the time we use gel, or we use a medium for a bigger electrophoresis. Yeah. So without the medium, only happens in capillary. So we can use free solutions like a buffer. Yeah? So I will explain the buffer. I will explain the capillary electrophoresis later. But first, since there are so many gel actually, I don't know which one to choose, but I think maybe I will introduce the non-native type, which is the Sds Page. So if you Google Page, it's very popular for electrophoresis. Page stands for polyacrylamide gel electrophoresis. So this is the native one. This is the non-native. Yeah? So non-native means that we use denaturing agent like a SDS. So SDS is sodium potassium sulfate. So it's something like this. So if you look at here, it's an anionic surfactant. So the reason why SDS is being used is because we want to get rid of the charge. Sometimes when you want to separate something, when there is a charge, it will cause the separation cannot be done, yeah, because usually electrophoresis is used to separate macromolecules. So when the size is so big, and when there is a charge, it's gonna be very clouded and it's so difficult to separate. So when something is so difficult to separate, we will use a surfactant like the anionic. Usually is anionic, and the easiest is to use SDS. This is the cheapest and maybe safest. So how we can do is we have to pre-treat the sample. Whatever sample you want to separate using SDS Page, together with the SDS, you just heat. Yeah, just heating. Heating will get rid the charge. Then after that, the separation only happens by size. Yeah, so like a gel, it's like a like a form of a lot of holes. So the small molecules will go through very fast, and the big molecules will get stuck somewhere and will move slowly. So in this case, we can separate by the size. Yeah? And then this is very useful, especially when we want to do protein purifications. And then we can also use it for determining the relative molecular mass of protein. Yeah? Because protein, the size is so different. So whatever we cannot do with HPLC, because HPLC it's not maybe until I don't know how many kilodalton, but for this one, usually when it's bigger, you can see the size is much bigger. It's like a gel. So this is just part of it. Like well, electrophoresis means you have to have electric supply. There is a anode buffer and a cathode buffer, and we separate them by like a chamber. Yeah. So, but the chamber have to be having some connections so that the electrons can move, the electricity can move. So usually it looks very big, something like this. I think if you Google from the internet, you can see a real, maybe in YouTube, it's easier to see and to see how people do the things. It's actually very big. Yeah, you have to use maybe 1 liter of gel maybe into the chamber. Then there's a negative. If you use the SDS, this will be the negative. So it will be a negative chamber and then the positive chamber. But anyway, overall, it should be something like this. So there will be, we call it the stacking gel, which is inside when the pH have to be different so that there will be a movement of the electricities. So, and the mixture of macromolecules will usually from up to down. Here, maybe it's difficult to see, but there is some space. So there is a space where we put the sample, and then the sample will go down to go down like this. Actually, it will follow the electrophoresis. How to say the movement of the electric. Yeah. So anyway, this is an overview of the SDS page. So it's quite similar, like we talked before, like a thin layer chromatography. So where we used the paper as the stationary phase. So in this case, the support is a gel. Yeah? So and the whole gel is being used to separate the thing. So if you imagine the gel, and previously when we talk about chromatography, the absorption will be based on the interactions. Yeah. So, but for electrophoresis, the interactions is mostly depending on the viscosity of the gel, of course, and the density of the gel. And another one is the electricity, the current, and the temperature also, it's quite important. Yeah. So meaning that it's it's mostly affecting by the gel. So and another one that you need to remember is the capillary electrophoresis. So in this case, it is not like a gel, it's like a free solutions. So free solutions means that it's more like a buffer. Yeah. So for capillary, there are many different phenomena. There are many different, we call it like separations type. The original one is called zone electrophoresis. And then after that is like the, this is like isoelectric focusing. So this is to increase the sensitivity. And then after this, Professor Terabe in Japan, actually, he invented this micellar electrokinetic chromatography. So in here, the missiles was used to move to have the electro-osmotic movement so that we can also separate the neutral compound. Yeah? So one thing you need to remember is usually in electrophoresis, we can only separate the charged compound. Yeah? Charged compound means like either negative or positive. Yeah? But in some cases, for example, the missile electrokinetic, when we use the missile, so the missile will be like, you know, will surround the charge, the molecule. In this case, there will be more interactions and the neutral compounds can also be separated. Yeah. So this is one of the invention. I mean, like a breakthrough in electrophoresis where the missile is being used and neutral compound can also be separated. Yeah. Because usually neutral compound will just go in one time. They will not be separated. So unless we have to use the missile to control the interactions between the neutral compound based on their size, then we can separate the neutral compounds. So this is like an extra, to add the extra interactions to improve the separations in capillary electrophoresis. So this is like an overall diagram. So for example, this is the detection windows, and inside the capillary, there will be movement. We call it EOF, electro-osmotic flow. So the flow will follow the electricity. Like for example, this is the negative, this is the positive. Yeah. So the positive charge compounds, ions, will move faster than the neutral one. Yeah. And the negative one will move even slower because there is a repulsion between negative and negative, and they will be pulled back by the electrophoretic movement, like the cathode here. So overall, the movement will be like positive, neutral, and negative. Yeah. So Beckman Coulter is one of the biggest or most popular maker for capillary electrophoresis. So I don't have CE equipment in my lab right now, but one of my ex-PhD students who later, the paper that I just sent you in chat. So Sasajima, he's working in the CLIMB lab. Later, I will explain a bit what we were doing in 2008, 2009, really long time ago, like more than 10 years ago. Yeah, more than 10 years ago. Okay. And okay. Inside here, when you open, there will be many chambers. Yeah. So when this is like a diagram of the capillary system. So the sample will be coming from, we have to inject the sample differently. So it's a bit complicated because depending on the maker, sometimes the sample injection is very difficult, but usually we just use a syringe to inject the sample. And usually the capillary will go through the buffer. So you just have to pass by the buffer between and connected with the high voltage supply like this. And then the detector will have to connect to part of the column. Yeah. So meaning that the column is an empty column because there is no column, just capillary. And part of the capillary will be inside the detector. And then the detector will connect to a data processor. Yeah. So when you look at a capillary system, usually they will write two sides. Yeah. One is they will write the length of the whole capillary like this. For example, 50 centimeters like this. Yeah. And then they will also write something like effective column length. Yeah. Effective column length means the column until the detector. Yeah. Because after the detector, whatever you separate, you cannot be detected. Yeah. So that's why when you look at a paper or whatever, usually we have to write effective column length. Effective column length means the capillary from this chamber until the detector. Yeah. So whatever after the detector is not counted for separation because the detection is already done before after the detector. Yeah. So please be careful when you look at the length of the capillary. So if you want to set up a system, yeah, look for you have to use a capillary which is longer than the effective column length in order to achieve the same separations. Yeah. Okay. And then the most important thing you need to remember is this one, EOF. Yeah. So without this EOF, there will be no movement at all. So we have to control the electro-osmotic flow of the whole system. The separations, whether is it fast or is it good or not, we have to control this EOF, which is the most important factor in capillary electrophoresis. So like I say, the capillary is made by fused silica. So if you look at inside the capillary, it will be something like this. Yeah, fused silica means they will be like silanol based. Silanol ions is negative charge. Yeah? So meaning that inside the capillary, in the inner wall of the capillary, they will be silanol based, and it will be all the negative here. So, and the electro-osmotic flow will, of course, it will flow through from the positive charge to the negative charge. Yeah? So, for example, this is the outlet, the cathode outlet, means there is a negative charge here, and this is the anode, which is a positive charge here. So, like I say, usually the neutral compounds will be in the middle and it cannot be separated under the usual capillary system. So comparing to the one monovalent, divalent will move faster. Yeah? So, and then comparing the size, if divalent, the small one will move faster than the big one. Yeah? So this is the usual diagram that you should remember. And usually the EOF together with the mu is the velocity. Yeah? So the velocity of the EOF will also determine the EOF is the same for all the ions. Yeah, but the what you call the electrophoretic mobility, I mean the mobility of the ions will be different based on their size and charge. So if you look at here, from the cathode here, the positive charge like this, it will be attracted to the cathode here. So it will be full like this. Yeah. So neutral, they will not affected by the charge. But the negative ions, they will pull back because of the repulsion. Yeah? So meaning that it will move back a bit, and the EOF, the mu app means the mu for apparent, we call it the apparent mobility, which is the real mobility, will be less. So meaning that plus will go first, and neutral will go in the middle, and negative will go later. Yeah. And then just remember the small one, even though in the same charge, will move much faster. And the same here, the small one with the negative charge, the small molecule will have less more effect, even though they have the same charge. So this is the movement of the ions, like imagination. Yeah. So monovalent will be, divalent will be faster than the monovalent, and the small size will be faster than the big size. So this is affected by we call it the EOF. Yeah. So previously, when we talk about ion chromatography, we have to reduce the laminar flow, right? Like the particle size in liquid chromatography, the particle size between this small area between the particle size can be reduced like this if you use the small particles to increase the separation efficiency, right? So meaning that in the liquid system, the flow, like we call it laminar flow. So this laminar flow effect will be reduced if we use a smaller capillary. But in capillary electrophoresis, it is driven by by EOF, the electro-osmotic flow. That means it is the same speed, yeah. And then this one we call it plug flow. So that means the peak in electrophoresis is very sharp compared to liquid chromatography. Yeah? So one of the main reasons we can see it's from this Van Dimter equation. Yeah? So maybe you remember Van Dimter equation, there are three factors, A, B, C, and A, B, C like this. So the plaque height will be affected by the A, which is multiple paths, the AD diffusions, and then B will be the longitudinal diffusions like up-down diffusions, and the factor C will be affected by the column. So in gas chromatography, there is no C factor, yeah, because there's not much column like. But in capillary electrophoresis is even better because there will be no AD diffusion, yeah. There will be no multiple paths. So the only factor B. That's why the peak is very, very sharp. Yeah? And then at the moment, the most important applications of capillary electrophoresis is the separations of DNA. Yeah? So, sorry, maybe this general protein. Okay. So the separations of DNA. So I want to ask you, maybe when you hear the words DNA, yeah, do you think DNA is charged negative or is it charged positive? Yeah. So DNA basically it's from 4 bases, right? I mean like guanine, cytosine, thymine, right? So all of this, it's having the amino base, right? So sometimes, I don't know, some students maybe think if this amino base maybe is positive charge, but actually, if you remember, the DNA is like a helix, yeah. So it's like a helix, and the adenine and I mean there are 4 bases, right? So C and T and A and G, they will combine together, and then it will be connected by a backbone, yeah, like a helix to form the helix. Yeah. So between, I have some examples. Okay, this one. Okay, here. So like, well, the purine bases are adenine and guanine here, and then the pyrimidine bases will be the thymine and cytosine here, but it will be connected with a phosphate backbone, yeah? And the phosphate here is charged negative, yeah. So meaning that the DNA is the net charge is negative, yeah. So, and for example, this is one of the example. We call it the nucleoside, the cysteine. So it is very complicated to separate DNA actually. So this is one of the example. It's crazy because one time you cannot finish, you have to separate we call it electrophoregram. So in liquid chromatography, we say chromatogram, right? But in capillary, in electrophoresis, we say electrophoregram. So this is the results of the separations. We call electrophoregram for the separations of uridine 5-phosphate oligomers. Yeah? So usually DNA is oligomers. So you can see when it is separated like this, it will be so crazy with so many peaks. So one time you cannot finish, you have to continue like this and then like this. So it's actually very long from here until here. It's very long, yeah, until 140 minutes. So this is the bigger the oligomers, the longer or the more peaks will be separated based on the columns ability. Yeah? So if you're interested, you can Google and you can learn more about this CE method. And okay, and from here, maybe I will introduce a bit of what we were doing before. So the title for this paper is so maybe you can see the PDF file. So if you download the PDF file, so this is well, we published in 2010, meaning that the experiment was done in 2009. So it's by Yasuhide Sasajima. So Sasajima, he was doing PhD under my supervision. At the same time, he was actually a policeman. He is working in the criminal investigation laboratory in Gifu prefectures. So it's like a crime scene investigator. So they were trying to develop some method to increase, to do some separations of drugs. Yeah. So the drugs here, we call it antidepressant. Yeah. Antidepressants, do you know what is depressant? If you read introductions, you can read the introduction later. Yeah. So it is a drug for people who have depression. Yeah. So when you feel very depressed, like stress, depressed, so when you are diagnosed by the doctor that you have depression, like in Corona now, yeah, many people will have depression at home because you cannot go out, and that's why you will have some mental problem. So in this case, in order to overcome your mental problem, the doctors will give you the we call it antidepressant drugs. And most of the drugs, the compound is like this, yeah. So it's like 3 rings, and sometimes 4 rings, and sometimes it's 5 rings, yeah. So this is the structures of the 20 antidepressants, which is in the market, yeah. Actually, there are more in the market that we cannot determine, but this is the one that has been approved by the government and also by the International Drugs Association as well. So the reason why the crime lab want to analyze this depressant is because some patients, they use these drugs to commit suicide. Yeah? So usually when a small amount of the drugs you can have is to cure your depression. Yeah? But sometimes when you take more than the limitations amount of the antidepressant drugs, you will kill yourself. So some people, they will try to kill themselves with these antidepressant drugs. And in the case of Japan, so the committing suicide case is quite a lot, comparing to other like accident, you know. So accident is not so many cases here. And sometimes maybe it is more popular. If you watch the drama or the movie, some people just use the sleeping pill. Yeah. So sleeping pill is also a form of antidepressants, yeah, because you take the pill and you relax your mind and you can sleep well. Yeah? So it is a form of antidepressants as well. And the basic compound is almost similar. Yeah. So, and in Gifu prefecture, this Dr. Sasajima, I mean, now he is a doctor. So at the time he was coming to the lab and to develop if you look at the title here, it's we call it simultaneous. Simultaneous means that we will determine under the same condition. Yeah? So if you look at the separation, so this is the separations that we also optimize the separations like this. And in here, compared to other electrophoresis method, what is the different or what is so special about here is instead of the buffer, we use organic solvent. Yeah? So we use just like a soda. Anyway, for the like I say, the total length it's like this. 112, but the effective length is only 104. So this is, and we use a very small capillary, which is about 5 microns in the diameter. So, and then, yeah, so the effective length is about 100 centimeter separations. So we optimize the conditions. It was very difficult to optimize the conditions because the structure is quite close. But we managed to do it under the condition when we used organic solvent to reduce the charge of the drugs, and then we could separate them nicely. Yeah. So this is the best separation results with quite good time. So we try to do it between 1 hour. Yeah. Because in the crime lab, if you want to analyze something, you have to repeat many times. Yeah. If one analysis take more than 1 or 2 hours, that means you have to spend so many days to do the analysis. Yeah. And so, yeah, so this is so these papers is about the optimizations of capillary electrophoresis system to separate 20 drugs. Yeah. And then here is the recovery results, like how we compare. LOD means the limit of detection, yeah? And LOQ means the limit of quantitation. Yeah? So RSD means the relative standard deviations. So the RSD actually have to be less than 10%. Yeah? So if you look at here, some of the drugs is very difficult to separate, and the RSD is more than 10%. But the limit of determinations and limit of quantitation is actually quite good. And then we could actually separate and determine the 20 drugs. So these are the other, we call it linear parameters and the reproducibility. Yeah? So if the results cannot be reproducible, that means it is not reliable. Yeah. When the result is not reliable, we cannot use the result. Yeah. So in here, we actually, it should be less than 5% for some drugs. Well, for liquid chromatography, usually we can achieve less than 5%. Yeah. But in this case, some of the drugs is difficult. So it's like 16 here, and then some of the, it's more than 10%. Yeah. But anyway, this is just part of the research for capillary electrophoresis. And then the main problem of the capillary system here is the detection. Yeah? Because the capillary is so small, so when it passes by the detector, it will be very difficult to detect in the capillary. Yeah? So in our system, we actually use a bubble cell. Yeah? So bubble cell means in it, like the capillary, the part of the capillary in the detector, we make it like a bubble. Yeah. So when the size is like a bubble, the quantity of the sample will be bigger for detections. So this is where we increase the detections. Yeah. So we also have another paper. Actually, it is in Japanese. Yeah. So because Sasajima told me he want to do online concentrations. So online concentrations is the method we used to increase the sensitivity. So if you Google online, there will be many words like stacking, you know, something like stacking, sweeping, or sometimes we call it dynamic pH junction or something like that. So most of the time you can Google with sample enrichment. Yeah? So sample enrichment in capillary electrophoresis will involve many different procedures. Yeah? So the easiest usually is like a bubble cell. Yeah? So most of the time now, the company, they will modify part of the column in the detector to become like a bubble so that we can increase the sensitivity. Yeah? So in our paper that Sasajima asked me to make for him is we use a multiple column detector. Yeah? detector flow cell. Yeah? So the flow cell that we put in the detector is we use a few capillary, and then we in the capillary of the detector we actually pack a small part like 1 centimeter of the packing materials to increase the like a stacking, So when there's a packing materials at the detector, the solutions with the sample will stuck in the place, and then it will be when the concentration is more and more, it will be able to detect. Yeah. So that is part of the we call it stacking. Yeah. But sometimes when we use the stacking, we also have to consider the interactions between the sample and the packing materials. Yeah. So it's a bit like a liquid chromatography. Yeah. So this is part of the paper that we published many years ago. So anyway, hi. So for capillary, there are some other parts that uh, so that another different kind of so that advantage. Oh, okay, maybe. Well, the advantage here is, yeah, like I said before, it's so the resistance of the electric field can be large, keeping the current, like the electric field we can control by controlling the speed and to improve the resolutions. Yeah. So, and then, for example, this is one of the DNA raw result of the DNA separations. So, like here will be the nucleotide number will determine like the combinations of the bases here. So at the moment, I don't know how many is the maximum to separate. Yeah, but usually I don't know. Sometimes when I hear people say 1 kilo Dalton or something, yeah. So 1 kilo or 2 kilo Dalton of bases can still be separated under. This is one of the raw results of the separations. Yeah. And then sometimes, in some cases, people will also use fluorescence, yeah, like when there's a multiple combinations. So sometimes, like I said, it is not so beautiful. I mean, not so clean, because it is difficult to separate when there is no column. Yeah, it is just imagine it is just solution. So it is very difficult to separate, and most of the time you will have overlapping like this. Yeah. So when there's overlapping, so for example, this is a nucleotide. There will be four uh, different structures. So some people will use the fluorescent label. Yeah. So we label the different structures with different fluorescence compounds so that it will come out as a different color for the fluorescence to improve the analysis results. Yeah. So in the same case like LCMS, yeah. So to do the separations or whatever, now the system is very advanced. You don't need to watch the system because everything is automatic. Yeah. After that, you get the data. That is the part you have very hectic. Yeah. Because when you look at the data, it's like this. You don't know what is what. So that is the part, is the hectic part. Usually you have to spend a few days just to analyze the results. So anyway, if now is a very mature method. If you with the corona, thanks to corona, many journals, they have the open access. Maybe you can read some papers, but future developments of the capillary electrophoresis will be like a lab on a chip. Yeah. So everybody is using a chip. If you Google microtask, is called total analysis system. It's like a lab on a chip, very small, like a 2 centimeter to 3 centimeters. So everything is on the chip. Labeling, sample injections, separations, everything is on the chip. Yeah. So in the form of chip, it is quite difficult because sometimes some people have to make different path length, yeah, to increase the separations. So even though, like for example, just imagine this is like a chip or whatever. So just one line to separate is not enough. Yeah. So people will try to make corner like this, corner like this, so that you can improve the separation length. But when there is a corner, you have to imagine the liquid, when you pass by a corner, it's more volume than the linear place. That's why the design of the chip is very typical. Yeah. So there are many people in big university like Tokyo University or maybe Osaka University. So anyway, microtask is now very popular, but it's very difficult to use, yeah, and the detection is not so good. But many people try to, because there's no other research you can do already. Yeah. So everything is getting smaller, everything is getting more expensive actually. So the more money you spend on many things, you can write and publish good papers actually. Yeah. So sometimes it's very complicated, because as a researcher, sometimes you don't know which direction you want to go, yeah, to go for basic research or to go for application research. Yeah? So I have this dilemma a long time ago. So I'm still having this dilemma, yeah? Because to have basic research is actually quite boring. Yeah? But without the basics, we cannot do the application. So that is why I'm still doing the column materials. I have been doing these color materials for more than 20 years, but still, the more I make it, the more I don't know how it is separated. Yeah? So anyway, next week I will share part of my results that I will summarize so that it will be easier. And because I only have 1 hour, maybe less than 1 hour, including the question and answer. And Rafi will be, his talk will be interesting. Maybe you can focus more on Rafi. Anyway, so I still have some time, so I will also share some of the advanced topic. Okay, okay, all right. Just maybe for the docent, and maybe for those in the future, if you are interested how the Japan give the fund to us in Japan. So usually we have these basic research programs. We call it grant in aid for scientific research under the JSPS. JSPS means Japan Society for the Promotion of Science. So most of us will try to apply for this fund every year, but usually it's just like, like Mora, maybe you apply for DICTI or DICTIS, this kind of fund. Yeah. So JST means the Japan Agency of Science and Technology. And this one, it's more like you have to have a pattern, yeah, like something you can commercialize. So basic research or application research or others, yeah. So applications research will be like JST Sentan. Sentan in Japanese means the most advanced, yeah. So JST most advanced programs will be something like this. And the final target is to commercialize and then to contribute to the society, yeah, to the market. Yeah? So, and some years ago, well, JST every year have different projects for many people, yeah. But there is one time, the procedure, actually JST is also under the MAX MEX is the Ministry of Education, Culture, Sports in Japan. So this is the main budget we got, yeah, for all the universities, including private and and public universities. Yeah. So anyway, so in one of the in some years ago, so JST have this open call for this development of systems and technologies for advanced measurement and analysis. So it was like in 2003 or 2000, I know, 2000, more than 5 years ago, 2015. So at that year, JST have 25 projects for this JST center. So the total of 25 projects was selected, and then 6 title is in the life science, and 8 titles is in the materials science. So, and then after that, 6 is in the environmental science. So just wondering, yeah, if life science, materials, environment, here, 5 more topics under what title, yeah? If you look at here, the biology is already here. Bio, materials, environment is already here, yeah? What else can it be, yeah? Well, the hint is after 2011, yeah. After the 311 incident in Japan, 2011, and this topic becomes very popular, very important, yeah. And it is a very typical topic, yeah. Okay, in 2011, remember the Fukushima, the nuclear plant accident. The last topic here is related to radiation measurement. Yeah? So radiation measurement is actually quite difficult, and it is dangerous, and the detections is very difficult. And so, so the total 25 projects. So 5 projects is under the radiation measurement. So if you Google this GSC Center, there will be a list for life sciences. Like if you look at the first one is a glycan analyzer, and then this is the 2-dimensional multiconfocal Raman microscopy. And then, sorry, here you can see 2D electrophoresis. Yeah? So 2-dimensional electrophoresis and the electro-blotting device. So blotting device means when you separate electrophoresis, you can see the band like a gel band. Yeah? So in order to determine the compound, we have to blot, like transfer the gel to, we call it Western blot. So when you transfer to Western blot, it's like a, to do the determinations. Yeah. So 2D electrophoresis means like a 2D liquid chromatography. There will be 2 different dimensions to separate the whatever compounds. Yeah. So this is by Araki Sensei in Kumamoto. So anyway, this is one of the, if you look at the title, most of it is the development of device, yeah, like X-ray, and this is the mass microscope, and this is the cell analyzer. Yeah. And glycan means the sugar, yeah. So the sugar analyzers. So maybe you know in the disease analysis, now diabetes is so bad in everywhere in the world. Yeah? So people who have diabetics will have more risk to have cancer, which will lead to a lot of different other diseases. Yeah. So anyway, so this topics is in the material science. So I will quickly go through. So material science is usually to do with how to like for example, this is the viscoelectricity measurement system. And then usually it's also like imaging to determine the materials. Yeah. So it will be more on like a microscope, like microscope in the air, real-time microscope for the SEM. SEM means scanning electron microscope. So most of it, it's deal with the imaging system. Yeah. For the environmental, quite similar actually, but the most important thing is carbon dioxide. Yeah? So carbon dioxide density and carbon dioxide monitoring. And now everybody is talking about carbon neutral. So later also I would like to share we have a symposium this week, Tuesday, Thursday and Friday. Later I will give you the link. If you are free, maybe you can join.
Yeah.
So yeah, anyway, I will give you the link later. Anyway, this is part of the titles for the environmental sciences. And then for the radiations, so it will be more on like the uh, the radio cesium in water, and then how to measure the radioactivity, because the important thing is there is no reference materials. Yeah. And it is so difficult to determine because there's no reference. So when there's no reference, how do you want to determine? So this is also part of this is also the difficult part. Yeah. And then another one is the Becquerel counter. Becquerel is the unit for radiation. So this is like the handy type, just to count the radiation. The unit is Becquerel. Yeah. And then this one is the like the handy Compton camera. Maybe in the airport, when you pass by, you have a thermograph camera to check your temperature. Yeah? So this Compton camera is to check the radiation. It's almost a similar imaging system. So this is to check the radiation. Another one is the gamma ray imaging system to have the ultra angle for high sensitivity. So these are the 5 radiations measurements topics in the JST system. So, okay. Anyway, another important things that I think everybody no matter, I think in the organic synthesis field, yeah, the MMR, the world highest MMR system actually in 2015, Japan, the NIMS. This is the National Institute of Material Science in Japan, together with GEL, the company. This is a Japan flag. So in 2015, Japan announced we achieved the highest MMR system in the world. So everybody is competing MMR. If you look at the MMR system, usually when you ask somebody, when they say, okay, I have an MMR, then you will have to ask how many megahertz. Yeah? The more the megahertz will determine your sensitivity and your price. Yeah? So usually the average is 600, 800. Yeah? So 600 maybe is normal, yeah, 400, 600, but the good ones is like 800. Yeah? So, and that time, 2015, the highest was 1020 megahertz. Yeah? But actually after that, so anyway, if you look at this is part of the development history of MMR. It begins from England, yeah, from Oxford, 500, 600, 750. Then after that, the German broker, they have here like 800 here. And then the red one is Japan. So from here, 900, 920, 930, I don't know. And this time is just compared to the broker is about 20 megahertz more. Yeah? But actually after that, in 2020, last year, broker already have 1,200. Yeah. So I think if you Google, it's in one of the, yeah, it's one of the, maybe it's, I don't know which area, but yeah, it's It's already 1,200. Yeah. So meaning that the important thing about this MMR is actually the magnetic field. Yeah. So if you look at the unit of the magnetic field, Tesla, it's so crazy. Yeah. 20 Tesla, 25 Tesla. Yeah. The normal magnet, you know that we use the normal magnet, right? For the for the notice board. Yeah. So the kind of magnetic is like 0.1, 0.1 Tesla, sometimes 0.2 Tesla. Yeah? The strong one, maybe the strong one is like 0.3. Yeah? But if you look at here, this is 25, So people can die, yeah? I mean, in this kind of magnetic field. So anyway, sorry. Anyway, sorry. For my for electrophoresis and some of the things I have finished for today actually. I think I have some questions. Yeah.
Yeah.
What was the questions again? Toxic level in the paper corresponds to so that it's correspond, yeah, almost like that, yeah. LD 50. Well, yeah, it's about LD 50 of each of each molecule, yeah. But some molecule they have actually different different level, yeah. So so that actually, if you look at the drugs, the more complicated drugs will actually have a more difficulty to do the separations. And then, like I told you at the beginning, this is the one we know, yeah. But there are so many illegal drugs in the market. And the illegal drugs, actually the compound is so similar, but it is so difficult to separate. And sometimes I heard from my ex-student, he said he's still having problem to separate some of the antidepressants. So usually they have to combine with the LCMS. Yeah. So now he also use LCMS to do all the separations. Yeah. And then MSMS, it's to have different fragmentations so that they can determine the molecule structure, the exact molecule structure to confirm the drug, whether this is the drug or not. Yeah. But different drugs will have a different lethal level. Yeah. So usually we use LD 50. Yeah. Yeah. So but I think, yeah, comparing to catalytic electrophoresis, I think still LC mass is more reliable, yeah. And in terms of the analysis time, and also, but of course, it also depends on your budget, yeah. So in a crime scene, in a crime lab, usually the budget is coming from the government, so they have enough budget, yeah. One of the frustrating point is because the crime lab, they have so good system, the material, I mean the separation system, and every 10 years they have to renew their system, yeah, and it's very expensive. So I asked Sasajima, I said, please donate your system to the university. but then he said, no, we cannot, yeah, because even though they deleted some data, there will be still some data left in the system, so they cannot donate to anywhere in the research center, even to National University, like in the same Gifu. They have to destroy everything. Yeah? It's so frustrating, So they have to just burn the money. Yeah? So as a researcher, I feel so frustrated. Yeah? So that is that is part of the law. Yeah. So whatever that is being used in the court or in the law, they have to keep for at least 5 years or more than that. And the data might left in the system, so they have to destroy all the system. Yeah. So that means they cannot donate to the university, which is, yeah. And the budget is so high. Do we have, sorry. In the paper is also mentioned about electrolyte and additive solvent effect. So what is the explanation for the effect? So comparing to the usual buffer, we used a non-aqueous sample that because the drugs, many of the drugs, they are not soluble in water because it's a it's like a lipoprotein drugs. It's more like it's more easy to dissolve the drugs in organic solvent. That is why we have to use some additive to improve the dissolve the how to say the sample solvation in the system. Yeah. So it is also to increase the interactions between how I say, like to control the flow of the separation also. So if you look at the chromatogram, without the addition and with the addition or with different acid, so different acid will have a different pH, and usually it will also having different so like a it's difficult to explain, but somehow we find it is very difficult because the strength of the acid is very different, even though we have the same pH. So when we compare the different additive, the separations was so different. Yeah? Another thing is the charge of the system was also very difficult. Yeah? So like for example here, we apply voltage 30 kilovolt, 30 kilovolt. Yeah. So we have a problem at the beginning to adjust the voltage because sometimes the noise will become so bad and we cannot even have a good baseline. So these are the optimum data. And then sometimes the additive, without the additive, it is difficult to even have a reliable or repeatable separation result. So, well, the mechanism is usually is quite based on the desorption and also some of the ionic interaction. Yeah. We think half is like ionic and a part is out of the hydrophobic. Yeah. We also control the viscosity, but in order to reduce the time, we try to use higher acetic acid, like 1 molar with some additive. The ammonium acetate, well, depending on what kind of salt, the salt is have to be volatile salt sometimes, but the detection depending on your detector. Yeah? So in our detector, we use the diode array detector, so which is based on the absorbance. So when a CE is connected to a mass, CE mass, we have to use very volatile additives. Yeah, because without the volatile additives, when we go to the mass, the interface, the ionization will be so bad and it will affect the detection results. So this paper is detected with the diode array absorbance. I mean the one that I think I explained before, based on the absorbance, the difference between the sample and the EOF. Yeah. Which electrophoresis method is the easiest to do? So, well, it's a gel electrophoresis is the easiest to do. Just use the page, amide gel, so that is the easiest. So you just need one chamber inside, then you put the gel, use the pH about neutral 6.8, another pH a bit higher, then you can have, but you still need to have a anode and cathode like a line to control the electro-osmotic flow. Can we use other instrument other than electrophoresis? Yeah, usually, yeah, for the drugs analysis, usually HPLC is more popular. Yeah. But yeah, CE. But the time here for CE is actually quite fast. It's faster. Well, it depends on three factors. Yeah, how much time you can spend, how much money you can spend, or how much accuracy, yeah, sensitivity you want to achieve. So yeah, so that will determine the cost also. Yeah. そうだね。Capillary electrophoresis comparing to the HPLC, the cost HPLC is very common, yeah. So it's quite cheap right now. And I think capillary is more expensive if you want to buy a capillary electrophoresis system from the market, yeah. But if you connect yourself, is the cheapest, yeah. So, but anyway, yeah, it's so I don't know. My how to say my supervisors. I mean, well, he's still of course my supervisor. So like my ex professor. Um, so he was the first person who I mean like one of the how to say the pioneers in Japan to do capillary electrophoresis, to do capillary liquid chromatography. So when he attend a conference in Europe, so Jorgensen is the person who first used the capillary electrophoresis to do the separations. Yeah. So you know, sometimes when you attend a conference, when usually the conference will be in a very famous place, like you know Firenze, like the very famous place. So he attended this conference in Europe, and there was when this Jorgensen was doing the presentation, my professor and his professor, so they were visiting the city, yeah. So they did not listen to they were not in the conference place, and so during their absence, and this Jorgensen just presented the first result in capillary electrophoresis, and the whole world was so surprised, was so shocked by the result, and especially with the peaks, it is so sharp, yeah. So my professor at that time, he got a shock because he was not there, he did not listen, and everybody was telling him this is the best separation in the world, and he got so shocked. I think after that, he did not want to do any research in capillary electrophoresis. Yeah. So sometimes, in Japan, we do not mix our research. Yeah? So because when we say, okay, this person, what is his originality? Yeah? So when we say, okay, ion chromatography, okay, this person is popular. Yeah? So when we say some research, this is the researcher. Yeah? So usually we don't do multiple research topics. So like I do capillary LC, the same capillary. Maybe CE is so easy, but yeah, I just not interested. I mean, I was told just to focus on LC. So my main focus is still LC, not CE, not GC, something else. Yeah. So yeah, we have to choose the instrument based on the cost as well. That's why it depends on how much accuracy you want to achieve. Yeah. LC mass can give you a very accurate result. Yeah. And of course, LC mask and LC mask with 2 masks is so expensive. Anyway, I still have sometimes.
Yes.
So anyway, yeah, I don't know, sometimes when you talk about the advanced technologies, like before I introduce the titles, when you look at this title, advanced technologies, what do you have in mind right now, after Corona? So for those who like cars, maybe Mora will fancy a car like this, So for men, usually you like to fancy a car. So when people talk about advanced technologies, you can imagine like a Lamborghini or something, Ferrari or whatever, So, but right now, maybe somebody know this is the Milky Way #2, the fastest super computer in China. Japan has one called K in Kyoto, but I don't know which is faster right now because everybody is competing to be the world #1. Sometimes, for people who like the electronics, maybe you can imagine, something like this. And this is quite in the near future, especially right now, like the Silicon Valley in the US. So everything is like you can control with just voice, like Alexa, do this for me, Alexa, do that for me, So AI now is so advanced, So, but of course, we also have to use, this is not Robocop, but we also use the advanced technique to improve and to cure some handicapped people. For example, this one is to improve the spine so that this person can walk again. So, but anyway, when I was some years ago, there was this person and this guy, maybe some of you don't know, he was the first man in the world to buy the trip to the moon. So this company, the human, what is the name of the company? What X again? So this is the not the government. Yes, I think he's one of the richest men in the world. So he has this venture company that realized the trip to the moon. So the rocket development, and they are already realizing this one. And the first auction for this company's trip to the moon was won by this Maizawa. Maizawa is the Zozo Town. Zozo Town is like Amazon site in Japan, one of the biggest shopping site in Japan. And well, it was so expensive, and then he was so famous that time, but now he already resigned from the company. I don't know why he resigned. He has a lot of scandal. So anyway, I sometimes when you look at, I don't know, different people have different thinking, but when I saw the news and this guy, he spent so much money to go to the trip, I mean, to relate the trip to the moon, sometimes we will think, so what, There are so many people who still cannot have enough food, but they are still, some people are making so, I say, stupid decision. But anyway, I hope many of you, learn, or maybe everywhere is talking about SDGs. So hopefully you can try to, in some part of your future, or maybe when you start to do your research, try to connect some of the topic to the SDGs. And in Japan right now, if we can relate our research to SDGs, it is easier to get the fund. So, well, there are many topics. For myself, we are trying to do the clean water here to determine to have some treatment, water treatment. and also to have affordable clean energy. One of my PhD students now is doing we want to do the determinations of biofuel, like the compounds, phospholipid in biofuel. But anyway, it is still difficult to do the detections. So if you want to know more about the SDGs, there's an app. You can Google SDGs and install the app and in your smartphone, then you can read more about SDGs. Okay, that's my final slide.
Okay, and there is also a question from one of participants, Prof.
Okay. I want to ask, we find the crazy pigs often may be run in the forensic lab. How do we calculate and determine from the crazy pig before? I still get confused. Usually we have to have some, we call it standard addition. Yeah. So when there are so many pigs, sometimes we just concentrate on certain pigs and we will, the crazy pigs usually we call it ghost pig. So the ghost pig usually will come out in the real sample. Yeah. So in the standard sample, when the reference materials, usually it's very clean. Yeah. The baseline is clean and the standard sample is clean. So when we have the real analysis from a sample, like a blood sample in a crime scene, if you have multiple other, we call it crazy pigs, like a ghost pig. We don't know what pigs is that. So at the time, we will do the calibration method to determine the compounds based on the retention time. Yeah? So usually there are a few methods we can use, like internal standard, like additional standard. Usually we will use the spike standard. Yeah, spike standard means that in the real sample, we'll add only the compound that we want to know. We add a bit and we take 3 points. Yeah. So when we take 3 points, so we add the standard compound into the real sample. So only the same pack, the same peak, the same time will have extra height. So and then we take the height, the absorption height, and then we plot, and then we can determine the original sample concentration. Yeah? So usually it's used additional calibration method, like spike method, yeah, to determine the concentration. But sometimes when there is a good internal standard, means that when you have so many samples, but you do not have the reference material for each sample. So in this time, we will add one internal standard and we will have the internal standard calibration and we use that calibration for all the samples. Yeah. So that is why the reference materials is very important. Yeah. And in some of the biological compounds, sometimes there's no reference materials. That it's difficult to determine. In this case, we only can compare with whatever we know, then we can see the difference. That is usually what we do. Yeah.
Okay, thank you so much, Prof. Lim, because we need using this Zoom to another visiting lecture. So I think we're gonna to close this. And before that, okay. Once again, thank you so much, Professor Lim, for an excellent explanation about electrophoresis. And this is very insightful and show us not only the basic principle, but also application of electrophoresis. And also thank you for participants who already joined and participating actively here. Hope you can get the knowledge. And as you can see in the participant list, there are 130 something participants. And normally we was attended by around 100 participants. So as you can see here, the participant who has named 20 XXXX, they are from pharmacy department of University of Muhammadiyah Surakarta. So welcome to our visiting lecture. This is the world-class professor program held by Department of Chemistry. And for your information, all the recorded version of this meeting you can see in the YouTube channel Departemen Pendidikan Kimia. Yeah, and also I want to invite you to this webinar. Please wait. I show you the poster. Yeah, here is the webinar will be held in the next week. Yeah, entitled "Current Application of Chromatography" will be delivered by Professor LIM. And also the co-speaker is Dr. Muhammad Rafi, and this is the last meeting held by Professor Lim, yeah. And time so flies, flies so fast.
Yes, so
okay,
fast.
So please register us, yeah, via this link, and we can see Professor Lim and Dr. Muhammad Rafi in the next week. Okay. So that's it. I think enough. Thank you so much for all participants here. See you next week and bye-bye. Thank you, Professor Lim.
Bye-bye, everyone. Bye-bye. Thank you so much for joining.
Yeah.